Alright, let's turn next to the third application of Bayes' theory, and that's a decision analysis problem. So consider the following decision problem. A firm needs to decide to develop a new product or stay with the current. If the firm stays with the current product, it makes a profit of 10. And if the firm introduces the new product, the firm thinks that there's a 50-50 chance that the new product becomes a hit or a flop. If it is a hit, the firm's profit will be 20, and if it's a flop, its profit will be negative 10. So often what we do in decision analysis, we draw the problem as a decision tree. And you can see in this decision tree you have solid dots, and a solid dot is a decision node. And you have hollow dots, and a hollow dot is a chance node. So the problem that I just read to you basically says we have to decide, shall we introduce the new or go with the current? If we go with the current, nothing happens by chance, we make 10. But if I introduce the new one, it can be a hit with probability 0.5 or a flop with a probability of 0.5. So what is my expected value? Well, the expected value of introducing the new one is, with a probability of 0.5, I can expect 20. And with a probability of 0.5, I make a loss of negative 10. So that is equal to 5, which is less than 10. So without any additional information, I would not introduce the new product, because the expected value of introducing the new product is less than what I have for sure, the current. But now let's consider the case that we can have access to perfect information. And we just quickly hold on to the consulting company that you can see here. So let's assume we could have access to perfect information. So let's assume initially you think, without any additional information, that the new product will be a hit with probability 0.5 or a flop with probability 0.5. And let's say you could approach a source of perfect information. Let's say God. God knows everything. So then, what is the expected value of perfect information? Well, I approach God with a probability that it's a hit of 0.5%. But now, God tells me 100% for sure it will be a hit. So what do? Well, I obviously introduce the new car and make a profit of 20. So then, times the 20. But if I approach God with a probability of 0.5 that it's a flop, and God tells me it will be a flop, of course then I go with the current and make at least 10. So then I have the probability of flop, because there's no uncertainty. God tells me, well, there's a flop. Then I go with the current and I'll make the 10. So the expected value of perfect information is 0.5 times 20 plus 0.5 times negative 10, which is 15. So now, how much are you willing to pay for perfect information? Well, the willingness to pay for perfect information is the expected value of perfect information minus what you have for sure. And that is our 10. That is what we have for sure. So the expected value, 15 minus what we have for sure, the 10. 15 minus 10, 5. So the willingness to pay would be 5. Okay, but we don't have perfect information, we have only imperfect information. And the industries responsible for providing imperfect information, those are marketing companies and consulting companies. So let's assume that we could consult a firm that looks at our new product, and they can create a report in which it says whether the company thinks it will be a success or a failure. Okay, before we go to the next bullet point, you have now a new decision tree. You have to make a decision. Solid dot, decision node. Shall I consult or not consult? If you do not consult, we already know you go with the current and you make 10. But if you consult, then there is a probability that the marketing company tells you it's a success, but we don't know that yet. And there's a probability that it will tell you it will be a failure. Then, depending on what the marketing company tells you, you have again to decide, shall I introduce the new product or go with the current? Well, if you go with the current, you make 10. If you introduce the new, it could become a hit or a flop. But if, let's say, you decide to introduce the new product after the marketing company tells you we think it is a success, so now the probability of hit is the probability of hit given that the marketing company told you, I think it's a success. So now what you want to know is, what is that probability of hit given that the marketing company tells me it is a success? Likewise, you want to know what's the probability or how does the information that the marketing company thinks it will be successful affect your probability that it's now a flop. What's probably happening is that if you get good news, like the probability of, like good news, the marketing company thinks that your product is likely successful, that probably increases your initial probability of 0.5 that it's a hit to something greater than 0.5. And likewise, the probability of flop, given that the marketing company thinks it's a successful, will probably fall below 0.5. But we could also be told by the marketing company, and they say, oh, I think that will be a failure. Then you still have to decide, shall I go with the current or with the new? But now if you go with the new, you have a new updated probability, which is, what's the probability that the new product will be a hit, given that the marketing company thinks, oh, this doesn't look too good, it's a failure. It's probably falling now below 0.5. And likewise, if you're being told that the marketing company thinks it's a failure, your new product, then you probably update that it's a flop to more than 0.5. So the point of this new decision tree is, you ultimately want to know what's the probability of hit given success. What's the probability of flop given success? This is where we need to apply Bayes' theorem. Okay, so let's just do that. The probability of hit given success. Well, that's the probability of hit times the probability of success given hit. Okay, so here we already know that the probability of hit, that is the 0.5. But what is the probability of success given hit? Well, this is a subjective probability. This numerator is the same as with perfect information. You approach God with a probability of 0.5, but then God told you it will be a success with 100% probability, or a flop with 100% probability. But here you need to think, if that market, what's the probability that when that marketing company looks at my new product, they somehow think in the back of their mind it looks like a hit. What's the probability that when they look at my new product and they somehow think in the back of their mind that it's a hit, that they conclude it will be a success? That is something that you need to decide subjectively. That is something which you cannot derive. This must be something that's given. And when earlier in the lecture we said there are three approaches to probability, one of them being a subjective approach, this is what we are doing right now. This is a subjective probability. You think that the marketing company somehow looks at my product. They don't say it, but somehow in the back of their mind they think it is a hit. Or if in the back of their mind they think it is a hit, you believe there's a 0.8% chance that they conclude it is a hit. So that is a 0.8. Well, the same applies for the flop. And we know that you initially approached that marketing company with a 0.5 probability that your car will, or your new product will flop. And now you think, okay, what's the probability that the marketing company will tell me we think it is successful when they look at it and actually think this is more like a flop, and that is 0.1. And again, this is what you think, so this is a 0.1. So those green probabilities are subjective probabilities. Okay, so now we already know 0.8 times 0.5, that's 0.4. 0.1 times 0.5, that's 0.05. So now the probability of success is basically answer the question, under which circumstances is there a success? Well, hit given success and flop given success. So there will be a success, 0.5 times 0.8, and with 0.5 times 0.1, you can expect a success. So this is the 0.4 plus the 0.005. That gives you the probability with which you can expect a success. So in other words, you approach the marketing company with a probability of 0.5, and then you think, okay, there's an 80% chance that they come back to me with success. So that's 0.4. But you also approach the marketing company with a probability of 0.5, but there's now only a 1% chance that they come back with success. So the total probability with which you can expect a success verdict by the marketing company is 0.45. And this goes here. Okay. So therefore, we still divide the probability of success by 0.45. You see, and then we get, for the probability of hit given success, we get now a probability of 0.89. So this one becomes 0.89. And likewise, the probability of flop given success, that's again the complement, that's 0.11. Okay, so now let's move to the other. Okay, so we also approached the marketing company again with a probability of 0.5. that it will be a hit. But now what's the probability that if they think it is a failure, that is again the subjective probability. So that is the point 2. So that is again subjective, point 2. Right. So you think, if they look into my new product, somewhere in the back of the mind, if they think it is a hit, the probability that they will write a report that says it's a failure is very slim, only 0.2. But on the other hand, if they look into my product and they look into it and they really don't like it and they think, oh, this is probably going to flop, the probability that they will conclude with a failure, that is now 0.9. And again, you just think. So, okay, so now we have failure, hit 0.2, and so now we can multiply again through. Here we had 0.5. And then for the numerator, 0.5 times 0.2, that gives us the 0.1. For the probability of flop given failure, we have to multiply 0.5 times 0.9, that's 0.45. So that means the probability of a failure, that sums up to 0.55. Okay. And now it's a probability of hit given failure, so 0.1 over 0.55, that's 0.18. And probability of flop given failure, that gets 0.82. Okay, before we move on, so what's important is that you do the decision tree. And initially you don't know anything. But if you want to know the probability of hit given success, for example, the first one, you apply Bayes' theorem. And that gives you the probability of hit times the probability of success given hit over the probability of success. The probability of hit is given, that is your initial probability. The probability of success given hit, that is something that you subjectively need to decide. And the same applies to the success given flop, the probability of failure given hit, the probability of given failure flop. Those are subjective probabilities that you need to decide. Once this is done, we can also calculate the probability of success and the probability of failure. So in other words, you approach the marketing company now with respect to failure with a probability of 0.5, that it's a hit, but then there's a 0.2 probability only that they come back with failure. So that averages out to 0.1. Then you also approach the probability with a probability of 0.5 that it's a flop, and now they come back with a probability of 0.9 that it's a failure. So there's a 0.45 and 0.1 probability summing up to 0.55 that you can expect a verdict of failure. Okay. And then the loop closes and you can determine all probabilities. Okay, so now that we have all probabilities, we need to decide what do we do. And so here again, we have our decision tree. And let me go maybe here. And now we need to decide, okay, now maybe let's go just out of the window quickly. Okay, so what do we do? If we consult and we get the verdict of success, shall we introduce the new or the current? So what we need to do is we have to calculate the expected value of the new given success. And that is new, so now we can expect with a probability of 0.89 we can expect 20, and with a probability of 0.11, negative 10. And that is 0.89 times 20. Maybe we can quickly ask Excel what that exactly is. So okay, so we can expect 0.89 times 20 plus 0.11 times negative 10, and that's 16.7. So the expected value here is 16.7, which means if we get a verdict of success, then the expected payoff or the expected value from introducing the new product is higher than the 10. So we can forget about doing this. And we can expect now with a probability of 0.45, 16.7. Okay, so this is what happens if we get a success report. And what about if the report says failure? Well, then we go with the current, we get 10. What's the expected value of introducing the new one, given that the marketing company thinks it's a failure? So now, with a probability of 0.18, we make 20, and with a probability of 0.82, we make negative 10. Well, that's definitely something negative, but let's just calculate it quickly. So now, if we introduced the new car, or the new product, I always think of a car for whatever reason, so that would be 0.18, have the equal sign, 0.18 times 20 plus 0.82 times negative 10. So that is negative 4.6. Well, negative 4.6 is less than what we go with the current. So if the marketing company tells us we think it's a failure, we will not introduce the new one. We go with the current. And it means with the probability of 55%, we can now expect a payoff of 10. Okay, so now what's the final expected value of consulting, or the expected value of imperfect information? Expected value of imperfect information. So it's not perfect information, but now we can expect with a probability of 0.45 to make a profit of 16.7, or with a probability of 0.55 we get the 10. Okay, so now we would calculate equals 0.45 times 16.7 plus 0.55 times 10. So that is 13.0115, which we see here, 13.015, which means that now we would have only a willingness to pay of 3.015. because we have 10 for sure, and the willingness to pay is the expected value from the information minus what we have for sure. So 13.015 minus 10 leaves us with 3.015, and yeah, that is what we would be willing to pay for. Okay, so I hope that this made it clear. So now we went through 3 examples of Bayes' theorem, and I hope you could see its usefulness. So let's just stop here, and then let's continue with combinations and permutations.